Hello everyone, thank you for joining this webinar on the Sundance Housing Co-op, which is a fabricated panel retrofit case study that's located in Edmonton, Alberta. My name is Betsy Agar. I'm a senior analyst with the Pembina Institute, and I'll be moderating this session. The Pembina Institute is a national non-profit clean energy think tank with offices across Canada. Today we're broadcasting from our Vancouver office, located on the traditional lands of the Tsleil-Waututh and Squamish nations. Leading Canada's transition to clean energy, Pembina works in several areas, including renewable energy, oil and gas policy, climate policy, and energy efficiency, including in buildings and urban solutions. Pembina's Buildings and Urban Solutions Group is led out of Vancouver and is guided by 5 core principles: electrify wherever possible, ensure all replacements go to high efficiency, liberate energy information to unlock big data and improve user engagement, go beyond cost effectiveness of energy savings, thinking about value of co-benefits, minimizing the pain points and risks so that we can unlock capital for everyone's benefit. So, towards liberating that information, we're pleased to host Peter Armour, the managing partner of Butterwick Projects, which is the contractor retrofitting the Sundance Housing Co-op. Peter has been designing and building energy-efficient houses in and around Edmonton, Alberta since the 1970s. He's a former partner in Habitat Studio, an Edmonton design-build company, and since 2007, he's designed and built 11 net-zero energy houses, including several that are generating significant surplus energy in Edmonton. Under his leadership, Habitat Studio has also built more than 50 houses with EnerGuide ratings of 86 or better under Canada's ERS rating system. He and his team designed and built Canada's first net zero energy affordable multi-family project and Canada's first net zero energy church in the Edmonton neighborhood of North Glenora. Welcome, Peter. We're looking forward to hearing about your experience using prefabricated panels for a deep retrofit of a multi-unit residential building.
Thanks, Betsy. Okay, I lost my screen here. What happened? There we go. Okay. Thanks very much, everybody. So we're at the beginning stages of a deep energy retrofit to a 59-unit 1970s townhouse complex in Edmonton. We've done our pilot phase, which is to retrofit the first building, a duplex, the one in the foreground here. So we're attracted to the concept of panelized deep energy retrofits for a number of reasons. We think it represents the lowest total cost of ownership. It should be far less expensive than a component by component replacement. It's higher quality, built in the factory. The systems are engineered, less disruptive to residents, easier for project managers to manage, and in total, just a better solution, a way to deliver a beautiful, superbly comfortable, healthy living. And probably the only way to affordably make existing buildings zero carbon ready. So the other side of the coin is that the way we've been doing retrofits, which is incrementally, is very expensive and can actually be a barrier to getting to where we need to be from a climate perspective. What happens when you replace just the windows, or you maybe add new siding with a little bit of insulation, and you don't deal with the air tightness and the junction between the windows? Is you get a bit of a mess that really not only is inferior in terms of durability, but also can prevent you from ever getting to where you want to go, because every time you spend money on these incremental improvements, that's money you don't have to do it right in one shot. And you also start to erode the business case. So the energy savings, you pick the low-hanging fruit, and that's no longer available for the business case for a full deep energy retrofit. So just a little history: the Sundance Housing Co-op was built in the 1970s. It's a 2x6 wood frame construction. The co-op has always been really far-sighted and proactive. When the buildings were built, the building code was on the verge of changing from 2x4 to 2x6, and the co-op collectively decided to give up closet doors so they could afford to meet the new code and do 2x6 walls. The way this project happened was that I was approached by 3 students from the Northern Alberta Institute of Technology looking for a capstone project. I helped them do blower door testing on a number of units. They did HOT 2000 modeling on enough units that they were able to scale up the effect of various energy retrofits to the whole co-op, and did a great job. And in the course of it, they introduced me to the energy sprung concept from the Netherlands, the idea of panelized deep energy retrofits. We priced the project, or they got pricing from the project from my now partner Dave Butterwick, to do the whole project, and it turned out to be about $5 million, and which was more than the co-op could afford or could convince its members to spend at that time, even though we would be looking after many long-term maintenance issues at the same time. But just by the way, the building in the foreground at the bottom there is the Riverdale Net Zero House, which we built in 2007 as one of the first net zero projects in the country. It was done under the CMHC Equilibrium program. Anyway, so the co-op was interested, but it was sort of at the extremes of affordability. But they were interested enough that they hired Renew Engineering to formalize the students' work, which was actually, and he did, and he hired me. This is Stuart Fix from Renew Engineering, also a partner in Butterwick Projects now. This project has brought us all together. But he did modeling in IES, and you can see some studies with infrared photos. I went around with him and we examined the buildings very carefully and found that really they weren't in terrible shape. There were some maintenance items that needed to be addressed, but not super urgently. They were going to be costs that were going to be incurred in 5 to 10 years for the most part. And so Stuart also did business case analysis on 4 different retrofit scenarios, and this information is all available. Although we are in the process right now, because our costs are being updated, of updating these scenario costings. We have way better data now. And again, you know, the budget, he got Butterwick Construction to price the retrofits, and it came in about the same as it did for the students. So then Enercan announced their R&D program, and we partnered with the Sundance Housing Co-op to go after one of these grants, and we're ultimately successful in doing that, and that made all the difference. And the co-op decided to go ahead with it, And in addition to the construction costs, there's also money in there for research, for information dissemination, and some of the engineering and design costs. So it really made it possible for us to go into it in detail, but it also gave us the responsibility to really document what we're doing and to make it available to anybody who wants to do this. So a little in detail around the co-op, there are lots of kind of anomalies. The mature landscaping is a problem for the digital capture. We've got fences, sheds, places where we can't get to the foundations properly, all kinds of anomalies. In fact, and little odds and ends. I mean, there's in the middle there we have some doors that are right tight to jogs. How do you add a panel in a space like that without shrinking the door, which is impossible. In fact, when I showed these buildings to Simon Verdun from Energy Sprong, who gave me a tour of some projects in Holland this spring, he looked at it and said quite cheerfully, "Oh, for us this would be a no-go," but we didn't have that option. The stars had aligned for us to do this project, and so we really needed to solve this array of problems. Probably there are easier buildings, there might be harder buildings as well, but one of the contributions of this project will be the solutions that we generate for some of these anomalous projects. So this is a summary of the before and after situation in terms of the building envelope and the mechanical system. There's almost no insulation in the basements right now. There's no insulation under the basement slabs, and there won't be at the end either. When we costed doing that, the cost per unit of energy saved was, even though it was a fairly big number, it was not sufficient to justify the intrusion that would be necessary to insulate on the inside of the units. We're adding about almost our 30 to the outside of the existing walls. We're adding another roof over. We're upgrading the windows. Our air tightness right now is going, and we've tested the first unit. We tested them before and after, and we started off with an average of 6.5 air changes an hour. We've gotten that down to 0.07. Not quite passive house, but a lot better. Now that's an envelope only test. We still have the old gas furnaces and hot water tanks hooked up, and dryer vents. So we're about, I think, 1.5 if we open those up. We put in HRVs, and so far our plan is to replace the furnace, but I'll talk a little bit more about that in a minute. So the first step really in the process is to get to make drawings of the existing building so that you can design the panels that you need. And for the pilot, we basically did that with a tape measure, but we've been working using photogrammetry and a program called Photomodeler with a company here in Vancouver to take a series of digital photos. You can see the camera positions in the upper image, stitching them together into essentially a 3D panoramic photo, so that we can then get a CAD-based drawing to design panels on. And we're working with a grad student on this who's making some progress. We're down, it's a lot of work, and it's a little bit we're still kind of in the 10 to 20 millimeter range in accuracy. We need to get that tighter. We think we can, but we're also working with LiDAR, with using digital capture with a Leica non-survey grade, like it's a expensive scanner, but it takes about 20 scans, and this is our next building. It starts with the point cloud in the top. You could then clip away all the stuff you don't want. You can see all the trees we have in the way. Makes the files totally huge. Clip away that stuff that you don't want, so you just get the building, and then we can use that to using a program called Undet, which is a SketchUp plugin to get a SketchUp model of the building, and we're in the range of 3 to 10 millimeters, so we're getting close. We still need to improve that a little bit, and from the SketchUp model, we make wood. We draw the panel drawings, and following on what we did what I learned in the Netherlands is we're generating. We build 4 separate drawings for each panel, and probably each panel will require its own drawing. On our next building, we'll have 20 panels. So the panels are, the drawings are as close to foolproof as possible, so that each station on the assembly line will have only the information they need at the time they're doing that stage. So there's minimal clutter, and right down to how the water resistant barrier gets applied, where the seams are, where the laps are for adjoining and sealing to additional panels, where the siding's going to go. We have a story pole for both. So we're pretty pumped that we've got this nailed. These drawings so far are not from the digital capture. They are from the original drawings, but it's a small step to adjust that. So the fit is really, really important. Like these panels are going to be built off-site, far away from the existing buildings, and the buildings are not necessarily level, square, or plumb. So, and one mistake in a panel that comes out with the siding on it, and the window in, you get a window that doesn't fit, will just stop a crew, and it'll be a crew of 6 with a crane, expensive operation, and just stop cold because a panel doesn't fit. Like it's a disaster scenario, and we just cannot contemplate having that. So we need to have all kinds of redundancy in the process to make sure that we get this right. And the digital capture, just from playing with it now so far, you see everything. It's way harder to make a mistake than if you're out with a tape measure and you're wondering which wall was that window on, etc. Anyway, so into the panel, we made a number of mistakes. The first was to dig the foundation insulation in by hand. That was hugely disruptive, and it resulted not only in disruption to the site, but we ended up having to restore the landscaping. And we're going forward. We're going to make that trench with a hydrovac truck and try to really minimize the site disturbance. The cost turns out to be better than we thought. But generally speaking, on the foundation, we're adding 6 inches of insulation below grade, and we've developed this box beam panel to support the weight of the panels. That's engineered with the straps to carry the weight that will be going on above. The walls on the pilot, we built the panels on site. It didn't actually take that long on my driveway. I live right next door, and put them up one floor at a time. We our details, I think, are generally good. We're happy with the way it all went together. We had no major problems. We think it's performing, that it will perform really well, and we've also got a bunch of moisture sensors in there so that we can test the moisture flows over this coming winter. But state-of-the-art fiberglass windows, rain screen siding, and we're relying on Casella Dorkin's Delta Vent S airtight, or it's a vapor open water resistant barrier that we're sealing the joints on the outside of, and that's where our primary airtightness is coming from. And then, I mean, just a few shots of the fun day when we were flying panels all the way around, all around. I mean, we've learned through this process. We've learned a ton. We have a sort of a log of ideas for improvements, little mistakes, things not to do again, things to do better. That lists, it's a Google Doc, 200 items long that we're incorporating into the planning coming forward, plus a sort of major mistake log, and we made lots of them. Time?
10 minutes.
Thank you. Okay, I think I can't even see my slide number. Okay, so anyway, so the insulation, I mean, you can see here, we basically are insulating between the existing wall and our panels as much as possible. We've tried not to take off the existing cladding. We probably took off more than we needed, but you know, on the whole site, the cost of removing all the cladding and disposing of the waste would be in the neighborhood of $300,000. So it's really important. I mean, that's one of the huge advantages of this panelized retrofit system, and a driver for some of the details. But we added a complete new roof over top. We wrapped the ceiling in a vapor barrier that's tied into the water resistant barrier at the corners. Here are a few of the details, but this is pretty routine for us. We have been working on airtightness since the 1980s, and as one of my carpenters said, "Oh, that's easy. You just need to think like air." And we're sort of in the habit of doing that, and so there was nothing particularly exotic about any of this. We used many details that we've used many times before. The only difference was we had some flaps where we had to leave holes that to install cellulose. I mean, that's one disadvantage of the system that we have, is that we basically have to install the cellulose on site, where a foam-based panel would come with all the insulation. You'd only need to do the air sealing. And you can see, you know, we've got a little bit of fancy footwork around the cantilever there, both for the panel support and air tightness and insulation. But again, these were not major problems for us. We set the windows back in. We were worried about the high risk of condensation if we left them out flush, which would have been a lot easier. But in our minus 30 design temperature, we're at high risk of condensation if we have the windows way out at the front. So we brought them in. It's good. It's much better thermal performance too. I mean, there's a net benefit, but it takes a lot more fooling around. So because we're now airtight, and because it's such I mean, I haven't built a house without an HRV since the early 1980s. It's a fundamental part of airtight of a low energy building, and a huge part of making healthy, comfortable houses. But in this case, we had to find places where we could run ducting to the second floor, and cut holes in the drywall in spots where we hoped there wouldn't be a plumbing vent or something like that in our way, and get that ducted down to the basement so that we could exhaust through an HRV, and then we used the existing furnace ducting to distribute that fresh air. So the plan is to ultimately and very soon abandon the natural gas line. Betsy mentioned the Pembina goal of electrification. That's what we've done with all of our net zero buildings. Is they're completely electric. But there's a fundamental problem here at the co-op. The power service to each unit is only 60 amp, and we need 100 or 125 to be able to run heat pumps and heat pump hot water tanks and get rid of the gas line. And that's going to require installing additional power service to each unit underground. And so we're right now in the midst of an engineering study and negotiations with our power provider to design and determine the lowest cost way to do that. But it's a major obstacle in our critical path because we spend a bunch of extra time and money working around preserving the existing gas venting and gas meters because we couldn't get rid of the furnaces. And now in phase 2, we're going to have to go back and take those out, seal those holes, and we really don't want to be doing that. So we've got to get this done, get the heat pumps in before we can proceed with the deep energy retrofit, because it's right in the way of the first step, basically. But the upside on all this is that getting rid of these gas meters, it costs in Edmonton to have a gas meter with no gas going through it about $650 a year. So for the whole co-op, that's about $38,000 a year. So there's a fair amount of capital released by the net present value of that, and that's likely going to go up as we move towards electrification. The business case for the gas utility is going to get worse and worse, and it looks and as renewable energy competes hard against that cost, they're not going to have room to raise the energy cost. They're going to have to make it on the cost of being hooked up. So we really think that $38,000 a year is really on the low side. So we're looking at two options here. One of them is to put in a single, likely Fujitsu air source heat pump unit with an electric resistant backup, because these things don't work very well below minus 25, which we have enough of in Edmonton. And we would put one on every, basically just plug one into the indoor unit into to replace the furnace, and every unit gets an outdoor unit, and that way all the energy is metered evenly. The second alternative is to put in a three-phase Daikin unit for every 4 units, because the Daikin units work fine down to our design temperature and wouldn't require the electric backup. So it's a we'll make that decision very soon and get going with this. But our expected seasonal coefficient of performance is about 2. So we get about 2 units of heat supplied for every unit of electricity. So we would also replace the air source heat pump or the gas hot water tanks with air source heat pump water heaters. We've had really good luck with these things. They seem to be providing lots of hot water and reducing the total amount of electricity to get it by a factor of somewhere around 1.8. So that's definitely part of a net zero carbon solution for us. So the costs are the scary part of this. The business case for this is really tenuous. We're not going to have the subsidy going forward. And just at a high level, it costs about $120,000 per unit to do the 2-unit retrofit. That was pretty much bang on what we budgeted, but we also budgeted about $85,000 per unit for the other 57. So we're assuming we're going to have economies of scale and improvements. It's a big jump, and it's turning out to be hard to get. We have a built-in geometry advantage because we go from a duplex to an average of 4 units. So there's the amount of panel area that we have in our other units is worth probably half the saving that we need to get. The rest we have to get from economies of scale, offsite manufacture, and not making the same mistakes again. So in budgeting for phase 2, we're finding that the information we got from phase 1 wasn't as helpful as it could have been. Part of we used normal construction divisions and the same kind of categories that we would have used for either a new house or a typical one stick at a time retrofit. And it really didn't give us the information that we need to really fine-tune the budget for phase 2. So we had to create a whole bunch of new budget categories that really reflect what we're actually doing. And we realized as we're trying to compare this back to the business case, because it's important to, in future projects, to be able to show the homeowner, the property manager, the building owner that they don't need to charge the cost of the insulation essentially against, that has its own benefit in terms of energy savings, but the energy savings don't have to carry the whole project, because there are huge advantages in terms of doing this maintenance all at once and putting in really durable components, rain screen systems and that kind of thing. But in order to sort of allocate the benefits that accrue from energy efficiency and to long-term maintenance and replacement, from that we really need to break the budget down some more. And so that's ongoing work that we're going to need to do, and that we will share with people. We've looked around at the Netherlands and a project in Ottawa and other sort of early panelized deep energy retrofits, and most of them seem to be going with foam insulation, and that has made us a little bit nervous. And but we really that wasn't the expensive part of the job, and it worked reasonably well. And we now have we're on a search for panel manufacturers. We found a small outfit that wants to start doing this. That we know these people quite well, and they have the facility and the knowledge, and are interested in starting into the panelizing business. And because they're not a dedicated panel manufacturer already, they're not locked into a particular form. And for example, we've spoken to a big gleaming production facility here in Edmonton with all kinds of CNC equipment and fancy German lines and stuff like that. And this just isn't turning out to be a good fit for them. We need panels that have to fit the building. We can't go with standard sizes. Some of our panels may even have to be built out of square. So far, we haven't run into that, but they're very particular. They have to fit the building. They've got jogs in them, and the factory would not. They're reluctant to take this on. So. And it turns out that the panel costs are less than 15% of the total. A lot of the money is in other parts of the budget, which we need to slice and dice and show where they are. Anyway, one of the things we've learned, and this also I learned from Simon Energy Sprung in Holland, is how important the people part of all this is. You really, and especially here because it's a co-op, you really need the buy-in of the members. And there are some people who are not yet convinced that they're the ones who need to be doing something about climate change. This is relatively low-income housing. There is going to be an increase in housing charge that will make sense over time, but for somebody who is elderly or just doesn't think long term, that needs some convincing, you somehow have to make, you need their tolerance and their trust, because we're working in their houses, we're working in their yards. It's we were lucky in the pilot. We got 2 families that were just amazingly tolerant and patient with us. But we need to reduce the amount of intrusion, shorten that period, and focus on making their lives better through this retrofit. There are some things that are automatic. Every window is a lovely windowsill. We're adding box bay windows to their living rooms that seem to be very popular. These houses, there have been people in Edmonton with their furnaces on so far, but not these guys. They're really thrilled with how even the temperature is and how comfortable it is. And we have to continually find ways to make it, more beautiful and better and shorten that disruption. And I mean, this is what it looks like from the outside. We still we had to do major landscape restoration, which wasn't quite complete with this photo, and it's still not complete now because we're going to be messing it up some more with the construction. And so, as part of our promise to NRCan, and from the very beginning, we thought, oh, they've been doing this in Holland. There must be great sources of information, and we were not able to find any of it. I thought it would just be there on websites or with links, but there it's being done by giant companies who are kind of they're fairly proprietary about what they're doing. So the information is certainly not being spread. One of my colleagues was there when we were in the first proposal stage and took a bunch of photos. So we have information from that. We have information from my own tour of a panel factory, but really there's no. So we thought that was a gap that we could fill with this project. So we have started an entity called Retrofit Canada with a view to hosting case studies, including all the details that people will share. We're completely open book about all of this. We're going to share our budgets, our costs, our construction details, our sad stories, and really with the hope that other people will reciprocate and put their projects on there so we can all teach each other, because we have no time to make this go. And one of the things that we're developing for that is a deep energy retrofit roadmap that shows how to go from the first to assessing the building, to doing the number crunching to find out if this is one that makes sense, and all the way through to panel construction. And we need to do this for not just this building type, but also for single family houses, for high rises, for commercial buildings. I mean, this is when people talk about the Green New Deal and the potential for green jobs, this is where they are. These are good jobs. They're interesting jobs. They're challenging jobs for anybody who really wants to make a difference every day they go to work. And we're counting on a generation of young, bright tradespeople to buy into this and help us with it. Thank you.
That's an excellent note to end on. Thanks, Peter. It's very inspiring future, I think, that you're projecting there. We have